In this video, we're going to look at our next numerical integration technique. We will start off with the same function as the previous video, so this is y is equal to x squared, defined on the positive x-axis. Now we're going to use the same limits as the previous video, so a is equal to 1 and b is equal to 3. So we want to work out the area under the curve y is equal to x squared from the limits 1 to 3. And we're going to again split this into 4 little segments, and you can see the segments here. Now the difference between this numerical integration technique and the previous one is that we're going to work out the area of each of these little shapes here. So the shape's going to be from here, and we draw a straight line from this point to this point. So we want the area of this shape, and then we draw a straight line from this one up to this point here, and we want the area of this shape. Now this little shape here is something called a trapezoid, and we can work out the area of the trapezoid using a simple little equation. So we multiply the length here, so this length here again is going to be our b minus a upon n, and then we multiply it by the height. Now to get the correct height, what we do is we add one side and then we add the other side, and then we divide it by 2. So that is, we take the average of each of the heights. So if we multiply the average of each of the heights by this length here, we will get the area of this little trapezoid. And we're going to add these trapezoids together in order to get the final area underneath our function y is equal to x squared from 1 to 3. So let's have a look at some of the mathematics. Now the value for the actual area under this curve is the same as the previous video, which is 8.667. Whenever we use the trapezoidal integration method, we're going to get a value of 8.75. So let's have a little look at this in terms of the mathematics. So I've written the actual algorithm here, and then I've put the values in at the bottom. So let's take a quick minute just to read over the algorithm. We're going to have our points, which are going to be our A, which is the starting point, and then we're going to have this next point here, 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 and the final point is B. So the first point is going to be A, and the last point is going to be B. Now to get the points in between, we just have to add on this distance. And we know that this distance is going to be B minus A upon n. In this instance, n is equal to 4. So we can get the x2 by adding the x1, b minus a upon n, x2, b minus a upon n, and that gives us these values here. Now whenever we look at the actual algorithm up here, we're going to notice that we're going to have the first point here, so that's going to be in fact the f of a, so that's going to be the height here. And the last one here is the f of xn, well it's going to be the final value, which is the f of b. But you'll note that all of the other values in between, they're multiplied by this factor of 2. Now we get the factor of 2 because of the way that we work out the area of a trapezoid. We said that to work out this area here, we have to add this length and then divide by 2. But to get the area of this one here, we're going to have to add this length again with this length. So that means that this length here in effect gets added twice. It gets added once for this area and added once for this area. And the same thing happens to this length and this length. So all of the internal lengths in effect are added on twice. So that's how you get this value of 2. Now another thing to note here is whenever we're multiplying by the value of dx, now we know that our dx here, it would be b minus a upon n, so that's just this distance here. But because again the way we work out the area of the trapezoid, we noticed that we're going to have a factor of 2, a factor of a half in, because we're going to be adding this height, and then dividing it by 2 to get the average, and again this height and this height, dividing by 2 to get the average. So if we take that division by 2 out, that division by 2 is going to be placed at this point here. So that means that this is our final algorithm for our trapezoidal rule. Now, if we were to use the example that we used in the previous video, again, the integral from 1 to 3 of x squared, using a symbolic integration here, we would get the value of 8.667. Now, if we were to work this out in terms of our algorithm here, we would have our value of x1, which is 1, and then we would have our x2, which would be 1 plus, and it would be b minus a upon n, so that's 3 minus 1 upon 4, so that's 1 plus a half, that's 3 upon 2, and then we would add another half on to that, which would be 4 upon 2, 5 upon 2, and the final one would be 6 upon 2, which is just our b value, which is 3. And then when we do the integration, we're going to have our b minus a upon 2n, so that's 3 minus 1 upon 2 times n, which is 4, so that's 3 minus 1 upon 8. And we're going to have our 1 squared for our first term, and then we're going to have our 3 squared for our last term. And then again, the terms in between are going to be our 3 upon 2, 4 upon 2, and 5 upon 2, and those values are squared, because that's the function we're actually operating, it's x squared. And again, we have to multiply them by this factor of 2. So this should give us the value of 8.75. So let's have a look at the assembly language code. This is our assembly language code here. I've put a little note at the top of the algorithm for the trapezoidal method for numerical integration. Now, we work out the value of our b minus a upon n, and we put it into register R5. And then we take our first value, which is the lower limit, and we put it through the x squared. So in effect, this is the working out 1 squared. This becomes f of x1, and we put it in a running counter in register R3. And then we do the final one, which is going to be our b value, and we work out our b squared. So in this case, it would be 3 times 3, which is 9. And again, this goes into the running counter. And then we work out the 3 values in between. And again, we set up the initial value of a, and then we run through each of the internal values. So it generates the internal value for our x, we work out the f of x, and then we multiply it by that factor of 2. And that's done here. Now finally, we take the final output, which is in register R3, and then we have to multiply that value by the b minus a upon 2n, and we generate the b minus a upon 2n here, and we do the multiplication. And then we store the final value in register R3 and also in a memory location called answer. So let's load this into the machine and see it running. I have assembled the code and loaded it into the RAM, so let's run the actual simulation. So we can see the simulation has started here, and the result that we expect to get is 8.75. So 8.75 in our fixed point is 08C0. So if this works out, then register R3 should have 08C0 in it. So we'll have a quick look down again just to see everything running. And I always enjoy having a look just to see all the lights flashing off and on. And we'll drop into the control unit as well. And the microcoded ROM. So everything is running as it should be. All of the sets enables for all of the registers are being pulsed here via the code within the microcoded ROM. So let me fast forward this to the end. It takes about 5 minutes for it to run, and I'll get you at the end of it with the result. Now the simulation has finished, and you can see here that we have an exact solution in register R3, which is 08C0, which is our 8.75, so it does work. And if we drop down into the RAM, you can see that we have a copy of the answer within a memory location. Now we could continue looking at other numerical integration techniques. For example, rather than joining the points together with straight lines, we could join the points together with little curves. So we could use a parabolic rule in order for us to generate the numerical integration. And this parabolic rule would converge quicker than the previous rules that we have just looked at over the last two videos. But we're not going to bother going any further into the details of numerical integration. Let's leave it at this, and we will move on to something else in the next video. So thank you for listening. I'll get you in the next video. Goodbye.